All right.
Get to see all my junk on my desktop, sorry.
Leave?
What's that?
The next talk is given by Russ George of Diffusion, Inc., San Francisco, California. The title of the talk is Experiment in Theory for Nuclear Reactions in Nanomaterials Show E14 to E16 Solid-State Fusion Reactions. And this one is being consolidated with morphology of fission gas bubbles in fissioning uranium metal closely. Okay, so I guess what I'll do is I'll let the bell go off.
Yeah, let me just see if it actually boots into PowerPoint like it's supposed to.
Russ, do you want a microphone? There is a lapel mic over there.
Oh yeah,
I think I can talk loud enough.
In fact, I should have been using this, I'm sorry.
You're okay.
Okay, all right, so I'll tell you what, at 18 minutes I'll give you a bell, and then a second bell at 20 minutes, and then you have 4 minutes.
Okay. This was a cartoon that came out 16 years ago on cold fusion when Pons and Fleischmann announced it, and people were somewhat alarmed that an exotic field like this could come into the world. And I'm going to talk today a little bit about results that I have gotten over these almost 16 years that I've been working in this field on nuclear reactions in deuterium-loving metals. And here was the Time magazine cover of 16 years ago when we were talking about cold fusion, and I crossed out the or illusion portion here since I think it is no longer subject to being considered an illusion. However, nobody knows what to call it, so it's been called cold fusion, solid state fusion, LENR, low energy nuclear reactions, CANR, chemically assisted nuclear reactions, you name it, it's nuclear fusion, with the difference, and the primary difference is that we don't see the expected high energy nuclear emissions, neutrons, gamma rays, and things. I prefer to call it solid state fusion. I think that's more consistent with where it occurs and how it occurs in matter. It only occurs in solid matter, especially in hydrogen-loving metals, including palladium and titanium and a few others. It's not a uniform bulk reaction in those metals. It's, in other words, when we run experiments with large pieces of palladium that we cut from the same stock where one works, and we'll take another piece from the same piece of wire, for instance, and that electrode won't work. So it's not a uniform bulk property of the metal. Deuterium is the preferred isotope of hydrogen for which this reaction occurs. To my knowledge, nobody's looked at tritiated systems where they've intentionally used tritium in the system to see if you get DT reactions or other things. Normal hydrogen, light hydrogen, appears to be a good null, a good control on this. No significant neutrons have been reproducibly observed to my knowledge. There's always been a persistent claims of some neutrons, but only at exceedingly low levels. Nothing like, if you have if you have DD going to He4 fusing, and you're making energy, it takes 10 to the 12 of those reactions to make 1 watt of excess energy. So if it was the conventional nuclear fusion pathway and 50% of those reactions were kicking out a neutron, we would have a vast number of neutrons. And with instrumentation that's capable of seeing a few neutrons per hour, we never see neutrons. Right now, some people have may claim something else, but probably nobody has ever claimed to see more than a few thousands of neutrons, even in the largest claims in cold fusion, nothing like 10 to the 12, right? And so neutrons simply haven't been observed. No energetic or gammas or X-rays have been reliably and reproducing, although some of the newer work is starting to show some X-rays.
Those were also low level. I mean, they were
Yeah, very,
soft.
and those are all very low.
It's a soft X-ray.
Right, and we've looked for the 23 keV palladium K alphas, right, X-rays that you would expect to see, and we even haven't seen those, right? Although they're perishingly difficult to see because they're so soft. Tritium is observed in a number of experiments, and ordinarily at dramatically reduced rates. So tritium experiments produce tritium maybe, I mean, I think the best tritium producers might infer tritium in 10 to the 8th tritons per second, something of that nature. Whereas helium-producing reactions are producing helium at 10 to the 12th helium-4 nuclei per second. So there's a big difference in that. There's a number of modalities of how cold fusion works that reliably are solid-state fusion. There's electrochemistry, which is traditional Pons and Fleischmann technique, and our mantra in our company is avoid electrochemistry like the plague because it is so difficult to work with in any consistent fashion and measurements that we don't do it. Glow discharge experiments, we typically use very low energy glow discharge experiments. We're now able to strike deuterium glow discharges in our cells with a fraction, probably about 1/10 of a watt of input power. And we're getting some interesting effects. Glow discharge is simply a way to get the deuterium atoms moving around vigorously in an environment where there are deuterium-loving metals, and we think that you can get microsite loading through glow discharge methods. And probably the best work in glow discharge has been done at Los Alamos by a group from the tritium group there, where they've seen dramatic online real-time tritium production from their glow discharge deuterium palladium systems. My that I like I've been working with a nanoparticle palladium. And given that palladium is not, we know the effect is not in a bulk uniform effect in palladium, it must be some micro effect. The logic has been that if you are buying lottery tickets on pieces of palladium that will work, the more pieces of palladium you have in a system, the more chances you have that some of those will be ideally suited to see these reactions. So as you reduce the particle size, you have more pieces of palladium for the same given material. So your chances of seeing these nuclear reactions are greatly enhanced by using lots of pieces as opposed to one piece of palladium. And sonofusion is a method that I've used for a number of years, which uses a collapsing bubble. And recently there's been news in the media of Russi Talyarkin's work, where he's using a collapsing ultrasound-driven symmetrical bubble that collapses in a deuterated liquid. He uses deuterated acetone. And we use various deuterated liquids. We don't do symmetrical cavitation, but we do what's called asymmetrical cavitation, bubbles where we collapse bubbles on surfaces. And we use that collapsing bubble to concentrate and load deuterium into those metals. And it's a very potent mechanism to achieve effectively instantaneously very high loading of deuterium in metals. And doing this, Scott touched on this, that this is probably a solid state phenomenon from the theoretical point of view. And so we've been looking at this, and we believe that the theories, and especially some of the things that relate to block states, are looking pretty good to us from a theoretical point of view as to how you might theoretically explain this. One of the interesting things about working with conventional solid state work is that the Coulomb barrier can be greatly reduced. And we know this happens in conventional solid state theory with electrons and with protons, which we know do conduct in metals in the same fashion as electrons. We have proton conduction is a well-known phenomenon. There's every reason to believe that you can apply many of the same solid state theories to proton conducting systems as you might for electron conducting systems. And it's with some hand waving because we don't understand the theory very well. we imagine that what happens in DD fusion is that you have a critical problem with cold fusion. Has always been the two problems that you had to overcome was how did you get two nuclei close enough together to fuse, to overcome the Coulomb barrier? Well, we think solid state physics shows us the way that we can get two nuclei together. The second miracle of cold fusion is once you get two deuterium atoms to fuse, and they're now in an excited state, they would typically come apart at a very high rate of speed, in something like 10 to the minus 17th of a second, which demands an energetic emission, fast particle emission, which we don't see. So how do you reduce that? How do you solve that second problem of cold fusion, that once you get fusion to occur, how is it that we don't have radiation, energetic emissions? Well, if the excited state di-deuteron helium-4 nucleus is entangled in a population of atoms, then it's very possible then that coupling can occur and the energy that would ordinarily be kicked out at a very high, in a very short time frame, can be smeared out over a longer time frame. And if you can smear that energy release out by a factor of 1,000,000 or so, you can jump from having to have a photon emission to being able to dispense the same amount of energy through a large number of phonon emissions. So thereby you can couple the nuclear de-excitation energy into the associated atoms, the lattice, through phonons, which is simply heat, which you simply observe as heat, leaving a helium-4 left. So it really comes down to the contrast in the two kinds of fusion, solid state fusion versus classical fusion, is that classical fusion is a collision of two deuterons in a collision space where you have to deal with isolated position of that resulting particle, and cold fusion or solid state fusion where everything is constrained in a solid state, so it's highly constrained. And we don't see the conventional mix. So jumping away from theory somewhat and showing you some examples of how simple the experiments are done. This is in nanoparticle fusion that I'm particularly in favor of. I worked a few years ago with Professor Arata from the University of Osaka in his lab, and he had taken sort of a hybrid. He took a conventional look at the Pons and Fleischmann system, and he said, well, we don't have a bulk effect in this palladium, so how do we improve the effect by basically using this particle concept that we have more pieces in it? So he hollowed out 2 pieces of palladium, which are small cylinders, and filled the interior of them with nanopowdered palladium, and then sealed them back up with an e-beam welding device, and then ran them in a standard electrochemical apparatus like Pons and Fleischmann. And we know that the interior gas, the deuterium goes into these cathodes, migrates through the electrode, and fills this hollow portion that's filled with nanopowder to an exceedingly high pressure of deuterium gas. So this inside, it's a dry, high pressure deuterium gas environment where the deuterium is coming through as dissociated Ds, right? Because deuterium doesn't load into a piece of palladium as a D2, it loads as a D, right? So, we don't know exactly the characteristics of the gas in that system, but we know that the pressures are extraordinarily high. And frequently these electrodes burst from the ultra-high pressure. Arata then measured online helium-3 and helium-4 and found large amounts of helium being produced in anomalous isotope ratios of helium-3 and helium-4. A few years following this work with Arata, and I'd been studying nanoparticles of palladium, and it turned out most of the literature on nanoparticles is all about nanoparticle palladium on catalysts, for hydrogenation catalysts, because in the commercial world, that's where the money is in palladium. You try to reduce the amount of palladium on a catalyst. You try to produce more smaller particles, which overall gives you less precious metal on your catalyst, same effect. So this experiment was run, these are 2 50cc stainless steel test tubes from Nupro materials, and they're filled about 1/3 of the way up with a standard hydrogenation catalyst, which for all the world looks like the charcoal that goes in a fish tank filter. and it has a 0.5% palladium on it. And wonders of wonders, when you have 0.5% palladium on carbon, the nanoparticles are the same size as Arata's nanoparticles that make work. This worked. We ran this at SRI using equipment provided by the Electric Power Research Institute of Palo Alto. We had an Extrel quadrupole mass spec. It's one of the biggest quads made. Very high resolution, high sensitivity instrument for helium. We were able to bolt this system up. It's pure gas phase, so everything was bolted to the instrument. There was a control. One of those test tubes had H2, one had D2 in it. They were simply heated to 200 degrees C, and we had good work. Here's the mass spec over here. Here's the two doers and data acquisition computers. And over a short period of 28 days, not so short, this is the data for the H2 cell of looking at helium-4 in the system. And this is the helium-4 in the D2 cell in real-time online mass spectroscopy with multiple controls and calibrated samples being tested constantly. The question was always, there's 5.2 parts per million helium in air. If you have a leak and air is leaking into your system, all you're doing is measuring the helium in air. Had that been the case, this line would have come up and leveled off. So given that here's air, we far exceeded that. There's no question that this is a online, real-time demonstration of the production of helium where there is none, with a control, right? H2, D2.
Is this the less case experiment?
Well, it's similar to less case, but it's an experiment that I ran, and we made substantial modifications, but it was with the cased catalyst. The catalyst provided by United Catalysts, which is an off-the-shelf hydrogenation catalyst, right? Typically sold by the train car load. And this was 1 watt per cc of anomalous heat with matching helium-4. So this is 10 to the 12 helium atoms per second for 28 days. So not a small signal, right? So I can jump through the. Scott's waving the clock at me.
No.
Okay. So
we're ahead of schedule.
Oh, okay.
Yeah,
Okay. So I'm a believer that block states in solid state physics are not for electrons only. They're also for protons, and in this case, deuterons are our more preferred states. We think that solid state physics takes us to this. I think that when you jump all the way down through this and you come to the point, that what's happening in the block state, Scott touched on Talbot's thing that you have effectively deuteron pairs forming. These might be analogous to Cooper pairs in superconductivity forming. The interesting thing about the difference between an electron in solid state materials and a proton or a deuteron in solid state materials is an electron, because it's very slow mass, has a very large wavelength. It'll fit into a large domain, right? A deuteron has a very small wavelength, so it's going to have difficulty being tuned to find the proper domain. One of the interesting things about cold fusion.
Sorry. You actually have more time.
And so if you remember this domain size and block states, it's the domain size is critical. Well, that takes us back down to. Turns out that the block state for deuterons, for proton or deuteron conduction, is ideally suited down in a particle, in a domain or a lattice domain, down in a few tens of nanometers in dimension. That's sort of the magic size, which just coincidentally fits our experimental observations that when we were searching for what material would work with cold fusion, we found experimentally that as we got down to the 50 nanometer particle size, we started finding that was a sweet spot. And it just so happens to coincide well with the solid state predictions as to where you ought to be. So continuing my survey of this is a sonofusion device that was set up at Stanford Research a few years, 95, I think, 96, on an experiment funded by the Electric Power Research Institute to demonstrate whether or not we could produce heat with the cavitation-induced loading of metals And this was another, this one device was here. This is a few years later, I took a similar device to Arata's laboratory in Osaka to run with his mass spectroscopy so that we could do more online work. Whoops, I jumped to. Here's the data from the EPRI experiment at SRI. This line, which is equivalent to where energy into the system is equal to energy out of the system with our calorimetry. The green points were control calibration points, so that we knew those were on the lines. All the red dots were experiments that we ran to see whether there was any anomalous effect. So, you know, often you learn a lot from your failures, so we can fail a lot and hit no energy, you know, hit exactly the same energy out as in, even though we're trying to succeed and make more energy. So, you know, we have the controls that we put in on purpose, and we have a lot of controls that we got that we didn't intend, but you know, a good negative result tells you a lot about your work. But some of these, we have a pretty good scatter above the line here that shows anomalous energy. And if you look at this, you know, here's a total energy out of something like 225 watts, and the energy in was like a little under 150. So there's 100 watts of anomalous energy being observed in that particular system. So there's a significant amount of energy in these systems. And to give you another clue about what happens.
Before you leave that, I was just wondering how big your error bars are on that graph.
The error bars are about the dimensions of those spots, right? They're very small. This was a piece of palladium target that was, it's about the width of a business card. So that's to give you an idea of the size of that. And it's in a volume of heavy water that's about 1 centimeter thick. And it's positioned halfway in that volume.
Probably should start winding up here.
Okay. So when we irradiate this with ultrasound, of which there's in the overall system there's 150 watts of energy coming out of the plug to the wall. But in the actual system itself, there's only a few watts of energy per square centimeter arriving as converted to the sound energy in the system. Here's a piece of palladium that melts, right? And palladium melts at 1600 degrees C. So how do you destroy material like this? We looked at this material using electron microscopy, and if we go back to this edge here and we pick out an area along this edge and look at it under electron microscopy, we found these features, a very, very disturbed surface. We found these kinds of features. It's blown up here.
That's what the kind of thing I showed. That's what Pam says. That's similar.
Yeah, and the Naval Lab known in San Diego has now essentially repeated this and seen the same observations. We find these little sputtered beads. These beads are about 1 micron in diameter. You can actually volumetrically calculate if you say that amount of metal melted at least in order to be removed, displaced from that, and you calculate the amount of energy it would take to simply melt that, you come up with a big number. Here's another little volcanic crater from another position. It was this one here. It doesn't have the sputtering. The metal is actually very smooth here, so we presume this metal came out much hotter than the previous one, so that it actually blew out as a clean surface, didn't leave sputtered beads. We just calculate the amount of energy roughly in this of how many 24 MeV DD fusion events would it take to melt that volume of material. If we just do first principles physics and say how much does it take to just melt that volume of palladium in the terms of fusion events, these are the kinds of number of events it takes to melt different craters, volcanic craters at that dimension. Volcanic ejective features, for years we thought we were really unique. We've found recently that they're found on nuclear metals, uranium, californium, other metals, have these identical features. It's the only other place in science where those features are observed is in cold fusion experiments and in spontaneous fissioning metal experiments. There's a series of things. Additionally, we looked at the helium from being produced from the systems. We also had a chance to look at the characteristics of helium inside the metal. This is helium bubbles created from neutron irradiation in metals. It's called loop punching. It's a classic nuclear process signature known to metallurgy. Here's a sample of our material, has effectively identical loop punching features in it that shows that that helium was born in that metal. Here's a piece of uranium, highly enriched uranium fuel with a fairly high quantity of plutonium in it. It's got the same loop punching features. So microscopically, physically, we can show that we have a nuclear process fingerprint that is identical to other nuclear process fingerprints in metals in this material, even though we're dealing with a material that's not a known nuclear material. Okay. Glow discharge. Scott's looking at me cross-eyed here. I'll hustle up. We do glow discharge experiments.
Okay.
Anyway, sonofusion and cold fusion, nanofusion, solid state fusion, whatever you want to call it, it's robust and reliable, and it's very reproducible, and it's producing hundreds of watts of anomalous energy in very small devices today. What's next? I've formed a company with a group of investors, and we're now beginning to fund projects both in North America and Europe to develop actually functional devices that we think will lead to practical applications in the very near future. Even though we've been at it for 16 years, people wonder how can we possibly think we're going to be able to deliver something soon? Well, it's been 16 years and we think the time has come. Here are some of the groups that we've worked with, where we've conducted experiments, who have supported us around the world. So we've had a pretty hefty group of collaborating scientific organizations assisting us in this work for 16 years. Scott talked about isotope anomalies. We've looked at isotope anomalies. We did neutron activation studies of samples of nanopowders. Here's dramatic study isotope specs, additional isotope effects.
All right.
I'm done.
Okay. Yeah.
I'd be happy to talk to anybody.
No, I mean, we do have time for, we do have time now for one or two questions. I wanted to make a comment. It's interesting, I actually, in my talk, I point out the nanoscale beginning at about 60, I did a calculation at ICCF, for ICCF 10, and showed that beginning at about 60 nanometers, characteristic dimension, you'd start triggering this stuff. And I now have, and you'll see in my talk, I relate this, there's been a phenomenon of triggering time, an incubation time. I've mentioned weeks, days to turn on the thing. Well, when you do it with it scales, from nanoscale, 60 nanometers, you actually do it in, the time that comes out is 5/100ths of a millisecond. And if you do it in something that's a micron size, 6 microns, it's 5 minutes. 60 microns, it's 80 hours. Which is a remarkable effect, and it's actually the onset of this ion band state conduction. You're going from insulated to conduction. I'm sorry, I shouldn't have taken so long. Are there other questions? Any questions? Comments?